Feynman didn't, I mean, there's no paper of Feynman's defining a notion of quantum algorithm, whereas there is of Deutsch, and there is actually the first quantum algorithm in Deutsch's paper. I guess Feynman sort of had it sort of upside down. He said, can we simulate quantum systems? And it seems hard to do, because if you have this few particles, then you still get this exponential state that you have to evolve and have to calculate, and this seems to be not doable. But nevertheless, nature seems to do it. And if you sort of turn that upside down, is asking, simulating it, you actually can ask the question, can I not let nature simulate something for me by evolving this exponential state in this exponential state space? Oh yeah. Let's see. So a quantum program or a quantum algorithm is nothing else than you start in a particular well-defined initial state, like your input and all the memory, all the qubits are set to 0. Then you do a unitary operation followed by a measurement. Like you measure a qubit, and the outcome of that measurement is the outcome of your computation. Okay, that's a quantum program. Let me briefly tell you, something interesting. When we do classical computation, well, Sasha showed that you have these bases that you can do, that you can define your circuits over, and we all know that if you have AND or a NOT, then you can compute any function with those three gates. Now, it turns out that quantum mechanically a similar statement is true. Namely, if I have a Hadamard gate, which is a 1-qubit gate, which we have studied already a little bit, and moreover, if I have this rotation over pi over 4, which is just this matrix, which is also a unitary, and I have this 2-qubit gate, which is a control NOT, which is actually a classical thing, which says that if I have this is the control wire, and this is the target wire. If this wire is 0, then this wire is unchanged, and if this thing is set to 1, then the value of this one is negated, and that corresponds to this particular.
The first wire is unchanged always.
And the first wire is unchanged always, but mind you, this is thinking about it classical, and actually it's not entirely right. But also this means that if I put superpositions into this thing, they will behave accordingly. Okay? If I have these three gates, then you can actually implement or approximate any unitary operation. So I can just use these three types of gates and build circuits out of them, and those circuits will be as powerful as if I had more complicated unitary operations. Okay, so these are a universal set of quantum gates. I won't show why that's the case, but that is nice, because now I can just define what it means to be efficient quantum algorithm, because of course before, if it's just this unitary, the unitary I have there could be very hard to implement, and would be meaningless. No, I say my algorithm is fast, or I have efficient quantum computation, BQP, if I can build a family of circuits again. Let's forget about the non-uniformity here. If I can if I can compute my function by just a polynomial amount of these gates, just like you define P poly. Here I have defined BQP poly. Okay, so then I have an efficient computation, and this indeed will correspond to something that you could, if you can control Hadamard pi over 4 and C naught on a reasonable amount of qubits, then actually, if you don't have too many of these to be done, then you can actually do this efficiently in the lab. Right? So this really is a reasonable definition of efficient. Okay, let me stop here.
Can full basis contain only one operator? Or is basis have two operators?
So it depends. If you allow additional variables, of course you can just combine this operation from maybe from different.
It's not clear. It's not clear.
Why?
Or it's not clear even in the classical case how to combine and and or.
But like you have a NAND gate.
If you allow multiple outputs, you have and then one and all.
One output.
No, but here you have multiple outputs. You know, so you can just make independent things on independent gates.
But if you have a NAND gate, then you get that
No, but
universal.
NAND gate is something artificial. It's not made out of according to some special.
I mean, you can do the trick here, like I have one gate, and if I put, I mean, I have another control which tells me which of these 4 or 3 is going to be. Right? So that would be one gate. I mean, you can sort of, I think,
But you can
trick.
You don't use controls for get information out of it. You can use only this gate.
No, what I mean is you have an additional classical wire which tells the gate what gate it should be.
But you don't have it. That's the question. You don't have it. You have just one.
What do you mean? I mean, I can.
You just have a source at once.
That's the question. Just one quantum gate, nothing else.
That would be one quantum gate.
So you can have a special git box that has the like 2 inputs that select like the function on 2 other inputs, and then you have 2 outputs from the gate and 2 additional outputs, which is
I
one.
want a 2-qubit universal gate.
I even think that it's 4.
Okay.
And on the 2 outputs there are classical 1 and classical 0, and the other 2 wires are the output of the gate.
Yeah.
You have a control thing and you have a real gate. So
I don't see why that.
but that's a classical well, argument, so probably it's more important in quantum field.
No, but the thing is, I will only put classical bits in the.
Well.
I will use it. I mean, I can make it.
Yeah.
But let's maybe finish here.
Okay.
Okay.
Let's.
Make an announcement.
I will make.
Lunch. No dinner. No dinner.
The lunch will be served in a cafe called Cyrillix. Bosphor, and it is located in the cross of, since it's called Deviative period.
Anyway, we should go there together.
Yeah, but still I will draw a little picture. So here is our university. Here is Большой classification. So turn to the left, then go to Sivtsa Brasa, to the left again, and then to the right. And the cafe is just the opposite the monument of Bulata Kudrawa. Near close by. This is called Deviative period, I guess. So, and the lunch is at 1:30, so we have 25 minutes. But of course you can come a little bit earlier. It is just downstairs in the back kitchen.
Сейчас, Коль, тут есть проблема, надо бы как-то закрыть вещи,